Hello everyone, I am Dr. John AROCKIARAJ, Vice Principal and Head, Department of Mathematics, St.Joseph's College, Cuddalore, Tamil Nadu, India. I am going to present you a simple topic on orthonormal vectors in a Hilbert space. First, let's see the definition. An orthonormal set in a Hilbert space is nothing but a mutually orthogonal unit vectors with the property stated here 1 and 2. If I is not equal to j, then ei is orthogonal to ej, and norm of ei is equal to 1. Orthogonal means the inner product is equal to 0. If H contains only the 0 vector, then it has got no orthonormal vectors. And how we normalize any vector? Just by dividing by its norm value, that will become a unit normal vector. This is the procedure. Now let's see an important inequality based on this orthonormal set of vectors in a Hilbert space. Look at this case. Let E1, E2, etc. En be a finite orthonormal set in a Hilbert space H, and if X is any vector in Hilbert space X, then H, then sigma I varies from 1 to n, square of the modulus of the inner product x comma ei is less than or equal to norm of x square. This is the first property. And the second property is that x minus sigma I varies from 1 to n, inner product x comma ei into ei is orthogonal to ej for every j. See how we are going to prove. First, let us try to prove the first inequality. Normally, all the norm value are greater than or equal to 0. So with that, we start the initiation. 0 less than or equal to norm of x minus sigma I varies from 1 to n, inner product x comma ei into ei, the square. Norm of x square is nothing but norm of x comma x. So based on that, we can write the same expression as two different values here within the inner product. Now, this can be written as 4 inner products, x comma x, and the second one is minus of sigma I varies from 1 to n, inner product x comma ei and its conjugate. Similarly, the third term, and the fourth term contains double sigma, double summation. And if you look at the last summation, when I keep constant 1, I as 1, vary j values from 1 to n, only ei comma ei, that is e1 comma e1 alone will be there, rest of the values will become 0. So when I keep I as with one value, rotating all the values for j, only one value is non-zero, other values are 0. Similarly, change the value of I as the next value. So for each summation, all the values are 0 except 1. So the double sigma will become a single sigma like the second or third term with the plus sign. Now the third term and the fourth term gets cancelled with the first and second terms alone. Look at the first term, that is the norm of x square, and the second one is with the property z into z bar is equal to modulus of z square. So use that property and take one of the terms to the other side, you will get the first inequality to be true. And to prove the second inequality, just take the inner product. When you take the inner product, the same case you are getting x comma ej minus and the sigma with that term. So when I keep changing the values of I from 1 to n, except one value, all the remaining values will become 0, which matches with the first value for j, and when they are in opposite sign, that becomes 0. Therefore, the equalities 1 and 2 are true. This is the Bessel's inequality for finite number of values. Now we shall see some more properties on orthonormal vectors. Theorem C is the Bessel's inequality, same thing for infinite number of values. And we shall see theorem D again with the same property just we have seen. Theorem D also can be proved. And theorem E is having a special property That is, every non-zero Hilbert space contains a complete orthonormal set. So we can find for everything, we can find it. Okay. So there is another result which is equivalent properties. If H is a Hilbert space and EI be orthonormal set of in H, then the following conditions are all equivalent to one another. EI is complete, X is orthogonal to EI implies X equal to 0. If X is an arbitrary vector, then X can be written as sigma inner product X comma EI into EI. And the last one, if X is an arbitrary vector in H, then norm of X square is equal to sigma modulus of the inner product X comma EI the whole square. Now, how the equivalent is proved? We prove 1 implies 2, 2 implies 3, 3 implies 4 and 4 implies 1. Cyclically, this will be made true. So first one, 1 implies 2. We assume the contrary. If it is the second condition is not true, then there exists a vector X not equal to 0 such that X is orthogonal to EI for every I. If we define E to be X by norm of X, then we observe that EI comma EI is an orthonormal set which properly contains EI, because that is a larger set, but that cannot be a larger because it is not complete. Therefore, this is a contradiction to the completeness. Therefore, if at all X exists, it should be 0. Therefore, 1 implies 2 is true. Now, assume X orthogonal to EI and X is equal to 0. That implies. So, by the previous one theorem we have proved. Anyway, consider the case X minus sigma X comma EI into EI is orthogonal to EI. Therefore, we get, if it is orthogonal to EI, the 2 implies the X itself is 0. Therefore, the vector that we have chosen X minus sigma is equal to 0, or equivalently X is equal to sigma inner product X comma EI into EI. So, the third property is true. Assume the third one is true. By the joint continuity of inner product, the expression 3 can be written as, because norm of X square can be written as X comma X. Now, just now we have shown from the third property, the value of X can be substituted as sigma X comma EI inner product into EI twice, and that is nothing but, take the scalars outside, and that scalars within that you will be getting EI comma EJ, and that becomes unit, and this is nothing but Z into Z bar concept. So, you will get modulus of Z square, and at last 4 implies 1. Assume if X is arbitrary vector in H, then norm of X square takes up that value. Suppose we have to prove that EI is complete. Suppose EI is not complete. It is a proper subset of an orthonormal set EI comma E. Since E is orthogonal to all the EIs, the fourth equation yields norm of E square is equal to, instead of X I am writing E, and that becomes what? 0. But we know that this is not 0. And this is a contradiction to the fact that E is a unit vector. What happens here? E is a 0 vector, but it cannot be a unit vector. Hence, what we have assumed, EI is not complete, is contradiction. Therefore, we have to go that EI is complete. So, we have proved cyclically all the 4 conditions. Therefore, all these 4 conditions are equivalent. Thank you.